Hi everyone, I'm Alex Wein, and I will be presenting some work on average case complexity of tensor decomposition. This will be kind of a quick high-level overview talk. If you'd like a longer talk with more technical details, you can find an hour-long talk on my website, and the URL is here on the slide. All right, so this talk will be about tensor decomposition, which is a basic algorithmic primitive that has a whole bunch of different applications throughout data science, machine learning, high-dimensional statistics, and so on. In order to explain what tensor decomposition means, I need to tell you first what a tensor is. So an order 2 tensor is just a matrix. An order 3 tensor is an n by n by n array of numbers. And you can have higher order tensors as well, but I'm going to focus on order 3 tensors for this talk. And we know that for matrices, you can have a rank 1 matrix VV transpose, which is built from a vector, as shown here. And similarly, you can have a rank 1 order 3 tensor, which is again built from a single vector. Now, the tensor decomposition problem is as follows. I'm going to give you a rank R order 3 tensor. So rank R means that it's the sum of R different rank 1 tensors. And the goal is for you to recover these components, the vectors A1 through AR. And for this talk, I'm going to focus on the case where the components are random. So we can imagine each AI is just a vector of IID random Gaussians. Okay, and the goal is just to succeed, succeed at decomposition, decomposing the tensor with high probability over these AIs. So, okay, why is this problem so important, and why is it useful for all these applications I mentioned on the previous slide? Well, one reason is the method of moments. So if I imagine I have some high-dimensional probability distribution I want to learn, but I get a bunch of samples, like a bunch of vectors drawn from this distribution, well, one thing I could try to do is build the empirical third moment tensor. And hopefully, depending on the setting, if I am able to decompose this tensor, the decomposition tells me something about the underlying parameters of my distribution. So let me talk about some prior work on this problem. So we're talking about third order tensor decomposition with random components. And so we have a bunch of positive algorithmic results, first based on sum of squares, and then more recently, some simpler spectral methods. So Maashi and Stoyer were the first to give a polynomial time algorithm, which has the state-of-the-art guarantees. And this is what the state-of-the-art guarantee is here, is that you can decompose the tensor in polynomial time when the rank is as large as this threshold n to the 3/2 up to polylog vectors. So that's the best algorithm we know, but information theoretically, you can do better. You can decompose a tensor of rank all the way up to n squared. And that's because this is the regime where the decomposition will be unique. So we have this kind of picture here. So I'm making a plot of R, which is the tensor rank. So the problem, it gets harder as you increase the rank. Right, it's quite easy to decompose a rank 1 tensor or rank 2 tensor. And so what happens when the rank is quite small, we call this the easy phase. So easy in the formal sense, meaning that there exists a polytime algorithm. When the rank is too large, the problem is simply impossible in the sense that the decomposition is not unique, and so no algorithm can possibly succeed regardless of runtime. And in the middle, there's this elusive hard phase where, in principle, you could solve it if you were willing to do some kind of brute force search over all possible decompositions, but we don't know a polytime algorithm. And so this is the main question I want to address, that when you're in this hard regime, is the hardness inherent? Is there really not a polytime algorithm here? Or might there just be a better algorithm out there waiting to be discovered? So this is an example of a more general phenomenon that we call statistical computational gaps. So this is not something that just happens in tensor decomposition, but really there are many different statistical problems that seem to have these hard regimes. Maybe the most canonical example is the planted clique problem, which is where I give you a random graph, so gn1/2, but then we plant a k clique, meaning that I pick k vertices and connect all of those to each other. So that's shown in orange here. But then I'm going to give you the graph on the right, which is the same graph, but just without the clique identified. And your goal is to find the clique vertices. So this similarly has these different phase transitions, whereas k, the size of the clique gets larger, you go from impossible to conjectured hard to easy. And so the difficulty with these kinds of problems is that, the current state of average case complexity theory does not allow us to say very much about these things, really conditioned on any kind of standard assumption from worst case complexity theory. And so we can't really hope to prove that this problem is hard, but instead there are various approaches that have been successful in recent years. So you can do certain reductions from planted clique. If I'm willing to believe planted clique is hard, I can use this to show a different problem is hard. You can also show unconditional lower bounds in restricted models, so showing that certain powerful classes of algorithms cannot succeed in the hard regime. And there are also some other approaches based on thinking about the optimization landscape or structure of the solution space. And so what do we actually know rigorously about planted clique, particularly in this hard regime? Well, one thing we are able to prove is that many particular classes of algorithms provably fail. So this includes statistical query algorithms, sum of squares hierarchy, certain MC methods. And the class of algorithms I'm going to mostly focus on today is called low-degree polynomial algorithms. So just to illustrate what this means, well, let's say I want to identify whether or not vertex 1 is part of the clique. Here is a degree 1 polynomial that may attempt to figure this out. So when I say a polynomial, I'm talking about a multivariate polynomial whose inputs are just all the input variables in my problem. So in this case, we're observing a graph. So we can think of the adjacency matrix as the input. And so I'm thinking about a multivariate polynomial and all the entries of the adjacency matrix, right? These are just 0, 1 values that tell you whether or not the edge is present. So some examples of low-degree polynomial algorithms. Well, here's a degree 1 polynomial. It just counts the the number of edges incident to vertex 1, so the degree of vertex 1. You could also take a degree 3 polynomial that counts the number of triangles containing vertex 1. And similarly, you can do other kinds of subgraph counts and so on. So we now provably know that this class of algorithms also cannot solve the planted clique problem when we're in this hard regime. So I want to say a bit about what makes the tensor decomposition problem a bit more difficult, or at least new compared to some of the existing results in this area. First of all, there's this issue of symmetry. So in planted clique, there is one particular clique that we're trying to find, and your goal is to find that one. Whereas here we have all these different components. We'd like to pose this as a question of whether you can find a component, but because of the symmetry among them all, the algorithm is not going to be sure which one it's supposed to find. And then maybe even a more serious issue is that many of the existing lower bounds, so for many of these different frameworks, statistical queries or sum of squares, low degree polynomials, the vast majority of existing results are really leveraging the hardness of a certain testing problem. So to illustrate this in the case of planted clique, well, the associated testing problem is, can you even detect whether the planted clique is present? So can you distinguish between just a random graph GN1/2 versus the random graph that has a K clique added to it? And the way that we can argue that, recovering a clique is hard is actually through arguing that even the easier testing problem is still hard. And for technical reasons, it's when we prove these kinds of lower bounds, it's kind of crucial that the null distribution is IID, or at least has independent coordinates, right? Which would be the case here for GN1/2. Now, for tensor decomposition, we are not going to be able to leverage the hardness of some underlying testing problem of this form. Maybe the first thing to try would be, well, let's think about, can you tell the difference between a rank R tensor versus just a tensor with IID entries, appropriately scaled to have kind of matching the first few moments. But the problem is that this testing problem is just much easier than the decomposition problem. And so we can't hope to use hardness of the detection problem to argue for hardness of the decomposition problem. So let me first address the issue of symmetry. And here, the solution is just going to be to define a slight variant of the model. So instead of thinking about the random tensor decomposition problem that I presented previously, I want to think about this version that I'll call largest component recovery. So we're given this 3 tensor, this n by n by n array, and it again has R components. But now the first component is going to be scaled by this 1 plus delta factor. So it has a slightly larger norm than the others. And you can think of this delta as being any constant. Maybe it's a small constant, or it could also be a large constant. And the AIs, the random vectors, for technical reasons, I'm going to take those to be IID plus minus 1 instead of Gaussian. And so the goal here, now there's a very specific goal for what we're asking the algorithm to do. Well, it's just supposed to recover A11. That is the first coordinate of the first component, where the first component is now distinguished because its norm is slightly larger. So here is now the main result. So like I alluded to before, I'm going to consider some restricted class of algorithms, namely multivariate polynomials, in the entries of this observed tensor. So we have polynomials whose variables are these t, I, j, k. And I'm going to ask about what is the best mean squared error that can be achieved by a polynomial of a certain degree, right? Where mean squared error is measured, with respect to this A11, the thing we want to recover. And here's the main theorem. Well, there's 2 parts of it. There's sort of the easy regime and the hard regime. So in the easy regime, this is saying when the rank of the tensor is small. So this is the situation where we know polytime algorithms do exist. Well, this is saying that polynomial of degree log n also succeeds. So succeeds to estimate this A11 quite well. On the other hand, in this hard regime, when R is bigger than this sort of threshold, n to the 3/2, then even if you take a polynomial of degree that's like n to a power of a small constant, then even then it will any polynomial has to fail to recover A11. Okay, so what's the point of this? We've shown in some formal sense that this transition from easy to hard occurring at rank equals n to the 3/2, that this is sort of real in some sense, or that at least it holds for a certain class of algorithms. Now, maybe I should say a bit about why this particular class of algorithms, the low-degree polynomials. So this is not really a new idea in this work. There's been quite a bit of recent work about it, and the reason why we think it's interesting to look at this class of algorithms is, well, first of all, a lot of powerful methods turn out to be captured by polynomials that's of degree logarithmic in the problem size. So this includes things like spectral methods or power iteration, includes AMP, which stands for approximate message passing, certain local algorithms on sparse graphs. There's a recent work relating this to statistical query algorithms. And so when we're able to formally prove that all polynomials of low degree fail to solve a problem, you can think of this as, well, we're rigorously ruling out certain known approaches. And because of this method has quite a good track record of predicting what we believe to be the correct statistical computational thresholds. Right, so for a whole bunch of different problems like planted clique and sparse PCA and community detection and so on, all these problems coming from high dimensional statistics, kind of the flavor of the problems I'm talking about here. Well, for all these problems, it's kind of now been shown empirically, kind of on a case-by-case basis, that, well, low-degree polynomials actually are as powerful as the best known polytime algorithms. And so when we prove failure of of low-degree polynomials, we take this as some kind of rigorous evidence for hardness. Of course, there are some counterexamples to this, and there's some caveats about, for what types of problems do we think polynomials are optimal. So sometimes low-degree polynomials can be beaten by other algorithms like Gaussian elimination or lattice basis reduction. However, these other algorithms tend to be somewhat brittle and not able to tolerate even a small amount of noise. And so in some sense, the low-degree framework is still saying something interesting or meaningful in these situations. And I'll also mention that by now there are results for low-degree polynomials for a bunch of different classes of problems. So this framework was first introduced for testing problems for distinguishing two distributions. And more recently, there's also been work on estimation problems, which is actually, recovering a hidden signal, so that this current work would fall into that category. And then also optimization problems, which means there's not a planted signal, but you're just trying to optimize some random objective function. So for example, I give you a totally random graph and you need to find a large clique. So I'll just wrap up with a few comments. So what's the main purpose of this work? Well, it was the first concrete hardness result for random tensor decomposition, really in any kind of framework. And so what we showed is that this class of low-degree polynomial algorithms is exactly as powerful as the best-known algorithms, best-known polytime algorithms. The key technical challenge here is that for this problem, the hardness is not explained by this testing problem of testing some planted distribution versus an IID null distribution. And so this required some new proof techniques, which I'm not going to get into now. I focused here on order 3 tensors, but really the results extend to tensors of higher order as well. And just to finish, I'll explain one open problem in this area that I think is quite exciting. So I talked here about random tensor decomposition, which means we're assuming the components of the tensor are random. But really, for algorithmic results, we'd like to make much weaker assumptions on the components. We just like them to be sufficiently generic, which can be formalized by a smooth analysis model. But the thing is, if you look at the best known algorithms that we have, for the random case versus the generic case, there's actually a significant gap here between what rank is achievable. And so the question is whether this gap is inherent. Is the generic case really fundamentally harder than the random case, or might there be a better algorithm for the generic case? And I'll stop there. Thanks a lot for your attention.